First there was classical mechanics, then there was quantum mechanics. Now, is there a new mechanics? This is a 21st century mystery keeping many physicists busy. Let's join the fun. Suppose you drop a ball from some height. How much time will it take to hit the ground? The answer is very simple. Assume you have measured the height in meters, divide the height by 5 and take the square root of the resulting number. The value you get is the time in seconds for the ball to reach the ground. For instance, say you drop the ball from 20 meters up, and the answer is 20 divided by 5, which gives 4, and the square root of 4 is 2. So the ball takes 2 seconds to reach the ground. We can actually perform an experiment by dropping a ball from different heights and measuring the time of fall using a clock. The measured time always tallies with the prescription we just used for calculating the time. Divide the height by 5 and take the square root. The same way, if we know the distance of a planet from the Sun, we can calculate how much time it would take to go around the Sun once. We take the distance of the planet from the Sun in centimeters, take its cube, multiply by 5 times 10 to the power 8, divide by the mass of the Sun in grams, and take the square root of the resulting number. And bingo! The answer gives the go-around time in seconds. You can check that for the Earth, this time is indeed 1 year. How do we know things work this way? Because the motion of objects always obeys definite laws of mechanics. For large objects that we see around us every day, these are the laws of classical mechanics discovered a few centuries ago by Newton and others. Large essentially means those things which we can see with our bare eyes. Dust grains, pencils, marbles, balls, chairs, tables, cars, trains, aeroplanes, satellites, planets, and stars. The motion of all these objects follows the mechanics of Newton. Things move along definite paths. If we know the force acting on a body, we can tell where it will be after how much time. It is of course true that knowledge of these laws is greatly significant for modern technology. How, for instance, could we design a car for smooth running if we did not know classical mechanics? Or how could we fly planes? Or how could we put up a satellite in the sky to receive and transmit our mobile phone signals if we did not know this mechanics? Does the motion of every object obey the laws of classical mechanics? No, a big no. Here, for instance, let us drop this pencil on the table. Can classical mechanics explain why it does not go through the table? No, it cannot. Let us switch on this flashlight. Can classical mechanics explain how the light gets emitted when we move the switch? No, it cannot. Nor can it explain why the TV picture comes up when we press the remote button, or how the cell phone works, or how computers do what they do, or how the eye and brain process vision, or how our headaches go away when we take a painkiller, or why the sky is blue, or why the sun shines. To understand these things, we need a very different mechanics discovered a century ago and known as quantum mechanics. It deals with the motion of very small objects such as elementary particles and the internal structure of matter. Elementary particles are entities such as the electron, the proton, and the neutron, which are constituents of atoms. The central nucleus of an atom is made of protons and neutrons, and electrons exist in orbits around the nucleus. Now, an electron in an orbit around the nucleus sounds a lot like a planet in an orbit around the Sun, but it could not be more different. If we try to explain the motion of an electron by the very same laws of classical mechanics which explain planetary motion, we fail completely, because classical mechanics predicts that the electron would emit electromagnetic radiation and spiral into the nucleus in less than a second. Planets, on the other hand, do not fall into the Sun. Classical mechanics works fine for them, and we simply cannot have a scenario where electrons reside in the nucleus. We very much need them in those orbits if we are to explain the results of innumerable physics experiments. All of chemistry depends on those orbits. The periodic table depends on those orbits. This is where classical mechanics fails and quantum mechanics comes to our rescue. Quantum theory tells us that we must look upon the orbiting electron in the atom not as a particle but as a wave, more precisely a standing wave which stays put at a certain distance from the nucleus. Different electrons stay put as different standing waves at different distances, and that is how the atom is made up. Moreover, the wave nature of an electron is not a figment of a theorist's imagination. It was established in laboratory experiments already some 90 years ago. So then, quantum mechanics tells us that small things such as electrons, protons, neutrons, atoms, molecules move like waves and not like the large objects of classical mechanics. The latter move along definite paths, just the opposite of what waves do. Waves tend to spread out in space from their point of origin. This is true for waves that form in a pool of water when you drop a stone in it. Same is true for sound waves and for waves on the sea. Yet, the electron wave is in a class apart from these other kinds of waves. These other waves are a disturbance in a medium, but the electron wave is not a disturbance in a medium. The electron wave is the electron itself. In fact, quantum theory says there is a wave associated with every particular object, even with a large object. However, because large objects have a very high mass, their wave nature is strongly suppressed. We saw that in classical mechanics, we can predict the future location of an object if we know its current location and the forces acting on it. Same way, in quantum mechanics, we can tell the future evolution of the wave if we know its current spread. In this regard, both theories are deterministic. The future is precisely determined from the present. The difference is that in the classical case, the deterministic evolution is of the particle moving along a definite path. In the quantum case, the deterministic evolution is of the wave spreading out in accordance with a precise law. The wave-like nature of small things explains just about everything that classical mechanics cannot account for. It explains the structure of atoms and molecules. It explains all of chemistry. The wavy motion of the electrons in a material explains the working of all of modern-day electronics and electrical machinery, the flow of currents, the lighting up of the flashlight, the working of a television, the computer, the cell phone, the blue of the sky, the shining of the sun, and much, much more. There then, for large things we have classical mechanics, and for small things we have quantum mechanics. All done? End of the story? No, exactly the opposite. We are about to enter some fascinating territory, a puzzle that has bothered physicists ever since quantum theory was discovered. The point is, the world of small things is not alienated from the world of large things. After all, large things are made by putting lots and lots of small things together. A table is made by putting together billions and billions of protons, neutrons, and electrons. Why then does the table behave so differently from a single atom? Why can a table not be in more than one place at the same time, unlike the electron wave, which spreads out to be everywhere? And by the way, how small is small and how large is large? A molecule with 100 atoms is small, all right, and a marble, which has some 10 to the power 23 atoms, is large. But how about a teeny weeny grain made of, say, a billion atoms? Is it small? Is it wavy? And does it obey quantum mechanics? Or is it large? And is it like the table? And does it obey classical mechanics? Or does it obey an entirely different mechanics? Remarkably enough, physicists do not know the answer as of today. Nobody has performed an experiment with a grain made of a billion atoms to find out which mechanics it obeys. Not that nobody is interested. Rather, such an experiment is extremely difficult to perform and beyond today's technology. The largest molecules which are known to obey quantum mechanics are made of some 10,000 atoms each. The smallest things which are known to obey classical mechanics are made up of about 10 to the power 16 atoms. For all things in between, ranging in size from 10,000 atoms to 10 to the power 16 atoms, we do not know for sure whether they obey quantum mechanics. It is an enormous desert which has not yet been tested in the laboratory. Why should we be so concerned? Do we really have reasons to doubt that quantum mechanics will not hold out when it is tested on larger and larger objects? And should not classical mechanics emerge as a limiting case of quantum theory? Here is where our story gets really, really interesting. The point is that small things meet big things and interact with them. That is how, for example, we learn about the properties of small things such as electrons by making what we call a measurement on them. A measurement involves an electron arriving at a measuring apparatus and, say, colliding with it. Say the apparatus has a pointer which moves from its rest position when the electron collides with it. By knowing how much the pointer has moved, we can work out, for instance, how much energy the electron was carrying. Or, in a more interesting example, we can use this device, or a detector as it is often called, to figure out whether the electron has arrived or not. If the pointer moves, the electron has arrived. If it does not move, it means the electron went someplace else. Now, the measuring device is by definition and construction a classical object which obeys the laws of classical mechanics. How else could we talk of the position of the pointer? We do not want the pointer to be in two positions at the same time. That will make it impossible to measure any property of the electron. If the pointer is at position A, we can conclude the electron has this much energy, and if the pointer is at position B, we can conclude the electron has that much energy. But if the pointer is at A as well as at B simultaneously, we cannot say anything about the energy of the electron. Undoubtedly, then, the detector is a classical object obeying the laws of classical mechanics. So we have a quantum entity, the electron wave, interacting with a classical detector. At this stage, all hell breaks loose. theory goes haywire. Why? Remember that a detector is not a wave. It is a classical object sitting at a definite position waiting to detect the electron. Let us line up 10 detectors in a row and mark them D1, D2, D3, etc. as you see in this picture. Now let us use an electron gun to fire out electrons slowly, one electron at a time. The first electron spreads out like a wave, and by the time the wave reaches the detectors, it spans all the 10 detectors. What happens next when the wave collides with all the 10 detectors simultaneously? Billion-dollar question. Quantum theory says that all 10 detectors must go click, each one of them registering the presence of a portion of the electron wave. The theory says that a superposed or entangled state of the 10 detectors results and must stay that way. It is a bit like saying that we have created a state in which a table is in two places at once. But of course, that is not what happens to tables, nor is that what happens to the detectors in this experiment. What actually happens in an experiment is the following. Only one out of the 10 detectors clicks. Which one? It is impossible to tell beforehand. It could be D3 or D6 or D9 or something else. And the detector which clicks registers the whole electron, not a part of it. The electron wave, which was earlier spreading out, now collapses to the location of one of the detectors. What experimentalists have found is that there is a definite probability for hitting a given detector. In the simplest of the examples, all detectors are equally likely to be hit, and the probability of a particular detector being hit is 10%. What this means is that if the electron gun were to slowly fire 100 electrons, one at a time, each detector will be hit by 10 of these electrons, but it is impossible to tell on which detector a particular electron wave will collapse. The collapse is a completely random process. This is an experimental fact which physicists have verified in their labs a countless number of times. Now this might sound a bit like tossing dice, but it isn't. When we toss a die, the outcome is random, and the chance of a particular number coming up is 1/6. The reason the outcome is random is because we do not accurately know the initial forces we apply with our hands when we toss the die. If we knew those forces, we'll be able to tell precisely which face will come up. There is nothing fundamentally random about tossing of dice. Randomness is a consequence of our ignorance of initial conditions. As such, the physics here is absolutely deterministic. It is our good old classical mechanics. It is completely different with quantum mechanics. The initial conditions are not random. On the contrary, they are known precisely, and the theory is deterministic. It is meant to correctly describe all processes involving electrons, including their interaction with detectors. So the theory says the electron wave should not have collapsed at all, and all the 10 detectors should have clicked. The theory does not predict the collapse of the electron wave onto one of the detectors, let alone in a random, unpredictable fashion. Where have the probabilities come from in a deterministic theory? We simply do not know the answer. This state of affairs is what led Einstein to famously proclaim that God does not play dice. The collapse of the wave onto one or the other detectors and the mysterious presence of probabilities in a deterministic theory has baffled physicists and philosophers alike for the last 90 years. Quantum mechanics is otherwise an extremely successful theory of the physical world, but this so-called measurement problem is like the proverbial fly in the ointment. Many resolutions for the problem have been proposed. Amongst them, three proposals stand out prominently as the most likely explanation. The first, known as the many worlds interpretation, says that collapse in fact never takes place and is only an apparent effect. When the electron wave hits the 10 detectors, the universe branches out into 10 branches. One of the detectors, say D1, clicks in our branch of the universe, and in the second branch D2 clicks, and so on. The experimentalist taking the reading also splits into 10 copies of himself or herself. Each copy of the experimentalist sees a different detector click. This sounds very fanciful, but this is exactly what quantum theory taken on face value predicts. The part which is still difficult to understand is the probabilities. Well, why is there a definite probability for each detector to click if no collapse has happened in the first place? The second explanation is known as Bohmian mechanics, which encodes randomness in initial conditions like in coin tossing. The theory says that the electron actually moves along a definite path and not as a wave. The wave does exist and satisfies the same evolution law as in quantum theory, but its job is to guide the motion of the particle in the sense that it carries information about the random initial conditions. The theory is best thought of as a different but equivalent mathematical formulation of quantum theory so that it makes exactly the same predictions for experiments as quantum mechanics does. Collapse is only an apparent effect because when an electron leaves the electron gun, it is already known which detector it is going to hit. Different electrons hit different detectors because of the random initial conditions. This is where the probabilities come from. Like the many worlds interpretation, Bohmian mechanics too is a perfectly logical explanation of the measurement process and cannot find faults with it. The third explanation is a theory known as spontaneous collapse, which says that collapse is for real, but that there is nothing special about the collapse that occurs during a quantum measurement. For every particle or object, large or small, the spreading associated wave undergoes a spontaneous collapse. For small entities such as electrons, the collapse takes place after an extremely long time, so long that it is as good as no collapse, and wave nature holds supreme, and the theory very closely agrees with quantum theory. However, For large objects such as detectors, pencils, balls, tables, the collapse happens so fast that these objects simply cannot be in more than one place at once. They are either here or there, but never both. The theory of spontaneous collapse then beautifully explains why collapse happens during a measurement. When the electron wave arrives at the 10 detectors and collides with all of them, it entangles with the detectors and forces them to form a superposed state. However, this state is extremely unstable and collapses very rapidly so that the electron is found in only one of the detectors and not in the others. The theory has an element of randomness built into the law of evolution, which results in the electron randomly going to one of the detectors, and the theory also correctly explains with proper mathematical reasoning why the collapse happens with a certain probability. Spontaneous collapse is then the new mechanics. It agrees with quantum mechanics for small things and it agrees with classical mechanics for large things. But it differs from both when it comes to explaining measurement and probability, and it differs from them very significantly for intermediate mass objects which are neither large nor small, say something made of a billion atoms. For such an object, spontaneous collapse would occur in about a millisecond without the need for a detector. This can well be observed in the laboratory if only we could make and maneuver such objects under controlled conditions. According to quantum theory, no collapse should occur at all. Hence, if physicists could study such objects, they would either confirm or rule out the theory of spontaneous collapse. Today, many experimentalists are working on cutting-edge experiments to find out if the idea of spontaneous collapse is correct. Hopefully, in the coming decade or two, we will know one way or the other. If this new theory is ruled out by experiments, then the answer to the puzzle of quantum mechanics lies in many worlds or in Bohmian mechanics, and we would know that nature does not play dice. On the other hand, if spontaneous collapse is confirmed, we would indeed have a new mechanics and a revolution in physics. Quantum theory would be replaced by a deeper theory which explains to us that collapse and probabilities occur because of the way this new mechanics works. Nature does play dice, but we would have understood why she plays dice.